Hello students, in this video we are going to understand the very important concept of the program status word, PSW, that is also sometimes called the flag register. And we have already touched upon this very important register in one of our videos. In this video we are going to learn in detail about the importance of the program status word and the central role it plays in modern day microprocessors by enabling them to implement powerful and complex conditional logic. So the program status word adds to the power of modern days computer architectures, and that adds a level of flexibility in implementing our complex algorithms written in high-level programming languages. So if you want to understand the power of program status word and the flexibility it gives to the processor in implementing your complex algorithms, stay tuned. Tech Instance has more for you at store, so I encourage you all to subscribe this channel and don't forget to hit the bell icon to receive important notifications. And if you have any questions, feel free to comment in the comment section below. But before anything else, let's clear some terminologies and historical aspects of the different word length of this register. As its name indicates, the program status word stores the status of the program. The program status word, or PSW, is a collection of data that is maintained by the operating system. This information tells us about multiple things or multiple properties of the currently executing instruction. Okay? So whenever an instruction is executed, it changes the state of the flag register. That is, it updates these flags. So the program status word actually stores some information about the currently executing instruction. Each bit in the program status word carries a very useful information that enables the processor to implement complex logic. As we said that the program status word is also called flag registers. So in computer organization and architecture, you might think of these bits inside the flag register as flags or some form of memory locations that can either be set or reset, right? Setting or resetting of these flags mean writing 1 or 0 to those memory locations. And in higher level language programming languages, keywords such as true and false are also used for readability. As the name implies that the program status word is of word length, which can be confusing because historically the word has evolved from 8-bit to the more powerful 32-bit and 64-bit machines. The 8085 microprocessor was an 8-bit computer with a flag register that was 8 bits wide. And in the context of 8086 architecture, the flag register was 16 bits wide with some extra information that we will see. So these are the bit information that you have in the 8085. It has the sign flag, it has the 0 flag, it has the auxiliary carry, it has the parity bit, it has the carry flag. But it doesn't have the overflow flag, right? That is there in the 8086 microprocessors. In the 8086 processor, we have more bits of information here, okay? Although x86 was originally a 16-bit architecture, the version in use today is the 32-bit extension. The IA32 term may be used as mentonym to refer to all x86 versions that support 32-bit computing. And the 64-bit variant of x86 is called x86-64. These are far more advanced processors than 8086. They have additional information in their program status word that are named as E flag and R flag register for 32-bit and 64-bit respectively. The nomenclature or the prefixes E and R identifies the register structure of these architectures. The wider registers, however, retain compatibility with their smaller predecessors, the 8085 and 8086. And for simplicity, we will consider 8086, whose program status word is 16 bits wide. Okay, so we have bit locations from 0 to 15, and these are the bits or flags that we had in the 8085 microprocessors. And we said that we are going to look into the 16-bit 8086 processors where we had additional flags. These are the most popular types of flags that we have. So the program status word consists of 6 conditional flags and 3 control flags. Okay. The conditional flags mostly have to do with certain operations in ALU, the arithmetic logic unit, meaning that not all instructions affect status register. Add and subtract affect all 6 conditional flags. increment and decrement affect all the conditional flags except the carry flag. Move, push, and pop do not affect any flag. And we will discuss each one of these flags in detail with examples so that you understand why these flags are so important to modern day computer architectures. Okay, let's dive deeper. So let us start with this very simple flag, that is the carry flag or the carry bit. So we know what does carry mean in mathematics, right? And this is the workspace where we are going to do all our examples and animations. So we know what does carry mean in mathematics, right? So if I'm doing an add operation, and if this operation results in generating a carry out from the most significant bit of the result, then the carry bit or the carry flag would get set to 1, meaning that an overflow has occurred. For example, if I add 1 to 15, I get a carry out from the most significant bit of the result, which signifies that the result is not correct. Since the carry flag can only be used with unsigned numbers or unsigned integers, we are assuming that these numbers are positive. And later we will also look into the overflow flag that is used with signed numbers. Okay, so that's what the carry flag basically tells us. Whenever you have arithmetic or logical operations, some special instructions that the arithmetic logic unit is performing on your inputs. So is there a carry out from the most significant bit or not? If there is a carry out, as in our case, there is a carry out from the most significant bit of the result, the carry flag in the program status word will be set to 1. If there was no carry out from the most significant bit, in that case, the carry flag would have been set to 0, right? So it's either 1 or 0, okay? Now, why is the carry flag important? Well, because carry flag is informing us in our 4-bit example in the workspace that we have, that since we can only represent a 4-bit number, the result is not the whole picture. Rather, it requires one more bit to append to the most significant bit to interpret the right result. But since we are not able to store that because we have no pattern for representing this value in 4 bits, right? Therefore, we need to perform some corrective measures to either correct or reduce the effects of this error. So the execution of some instructions can potentially change the carry bit value in the flag register that might indicate some problem like incorrect result. Okay, I hope that was simple. These are the related instructions used with the carry flag. JC, jump if carry flag is 1, and jump if carry flag is 0. JC and J and C. And these are other direct manipulations used with this flag, with the carry flag. STC, set carry flag to 1, CLC, clear carry flag to 0, and CMC, invert the carry flag value. Okay. Next in line, we have the parity flag. That simply indicates whether the number of ones in the result register is odd or even. And as we know that in most of the architectures, the result is stored in the accumulator register. So if the count of ones is even in the, so if the count of ones is even in the result register, the parity bit is set to 1. Otherwise, that is set to 0. So you might be thinking, what is the use of this bit? Well, this bit or flag is mostly used in implementing error correcting and error detection code, a very specialized area in computer science and electronics. And the parity flag is the simplest form of detecting errors. Suppose that we have some value that we have in the accumulator, and because the number of ones is even, the parity flag would be set to 1. And suppose that there is a sudden voltage spike in our processor that has changed 1 bit of the accumulator from 0 to 1, and hence changing the count of ones in the accumulator to odd. That would set the parity flag to 0 because the data gets corrupted. Now we can detect this kind of errors using the parity bit. So what do we do in this case? One option is that we can reload the data from the memory. So this parity flag is used to detect errors if there is any errors or modification to the result. And these are the related instructions used with this flag. JP, jump if parity flag is equal to 1, JNP, jump if parity flag is 0. Similar to the carry flag, we also have the auxiliary flag. If we add two 8-bit numbers, a carry may be generated from the lower to the higher nibble. Such a carry is called intermediate carry, also known as half carry or auxiliary carry. This is used with 8-bit operations, as we are talking about the packed BCD. That is more efficient than its unpacked BCD counterpart. Auxiliary carry might seem useless for a while until you watch my earlier video on binary coded decimal representation and the concept of how a BCD arithmetic works. So auxiliary carry is extremely useful in performing BCD arithmetic operations. Okay. For example, let's say that we have 46 and 45 in decimal and we add them to get 91. And these are their corresponding binary coded decimal numbers. We have the lower nibble and the upper nibble. And when we add them, we should expect to get 91, right? But what we get is not according to our expectation, because we get 8 in the upper nibble and 11 in the lower nibble. And we know that we cannot represent 11 in binary coded decimal because we have only 4 valid bits, and we can only have patterns from 0 up till 9. I hope you remember that from my video on BCD. And also notice that we don't have any carry from the lower to the upper nibble. So now we have two things. One, the auxiliary carry flag is 0. And two, the lower nibble of the result cannot be represented in the available legal BCD codes here. And here is what I call the golden rule that comes in, right, and solves the problem for us by adding 6 to the result, and we get 91, right? So auxiliary carry plays a key role in BCD arithmetic. And our golden rule also points to cases when we actually have an auxiliary carry flag set to 1, right? Next, let us learn other more interesting flags that are used in implementing more powerful and complex logic in our machines. So there is this flag called zero flag, which is a very simple flag, but often simple ideas prove out to be very powerful. So if our accumulator value equals to 0, or the currently executing instruction sets the destination to 0, then the zero flag is set to 1. And it is set to 0 otherwise. Those who have watched the video series on x86 assembly crash course would not be wondering, how can this very simple logic be very useful, right? Let us understand this flag in more detail. Let us assume that I have this program that is executing, and I have this very popular instruction, JZ. JZ stands for jump if 0. Jump if 0 flag is 1. JNZ, jump if 0 flag is 0. And JE and JNE, jump if equal or jump if not equal, which is alternatively used with the compare instruction. So the JE instruction actually checks whether the result of this comparison is 0 or not. And that check is performed very easily by checking the status of the 0 flag in the flag register, because we know that this flag will be set to 1 if the result of the comparison instruction is 0, right? And after this check, if the flag value is set to 1, then what the JE instruction actually does is that it will not execute the next instruction. Rather, it would jump to the address specified by label .L7. So the execution of this instruction could potentially change the address in the program counter, right? I think that should be very easy by now. But why would we want to ever use this? Well, this is used in implementing what we call conditional statements in your high-level programming languages like C, C++. For example, if you want to write an if-else condition statement, you would certainly have to evaluate certain condition based on which a particular block of code would get executed. It could either be the if part or the else part, right? So conditions such as x is equal to y, then do this, else do that, right? Similarly, if you have a for loop, you can say as long as I is greater than 0, execute this code block, right? As soon as I becomes 0, the program directly jumps to another location that skips the code block inside the loop, right? So to execute any conditional statements like if else condition statements, while and for loop, and switch statements in C programming or other high level languages. This is how our compiler actually converts our programs into machine level language that uses instructions like JZ, JNZ, JE, and JNE, etc. So without these jump statements, it's very hard to translate such high level constructs into machine language. And the zero flag plays a very important role here. Then we have another very simple and useful flag that is called the sign flag, okay, or SF. This flag is used with signed numbers, that is signed integers. So in 2's complement representation, if an arithmetic or logical operation is carried out on signed numbers, the status of this flag is set to 1 if the most significant bit of the destination is 1, okay? And like the zero flag, sign flag also helps in comparing between two numbers. So how does the sign flag actually works? Well, in simplest words, this flag is set to 1 if the value in the destination is a negative number. And we know that in the 2's complement, if the most significant bit equals to 1, then the value is negative. And if that is 0, the value is positive, right? So the sign flag is updated by whatever value is in the most significant bit. And if we had a positive number, the sign flag would have been 0. These are the related instructions. JS jump if sign flag is equal to 1, JNS jump if sign flag is equal to 0. And both are used in combination of decrement and increment instructions. So once again, this flag is often useful when you have signed number representation, when you are dealing with signed integers, okay? For example, you have a signed number 12 that is moved to the count register ECX. After the loop body is executed, we need to update the value of this counter by using the decrement instruction. And then we need to check whether we need to execute the loop one more time. The two instruction sequence are combined to form a single instruction called the loop instruction. However, the performance of the two instructions working in pair are more efficient than the loop instruction. So this example shows us the usefulness of the sign flag in controlling the flow of the loop. For more on signed and unsigned integers, we have two detailed videos on 2's complement that explains signed and unsigned arithmetic. One of the videos talks about the surprises that 2's complement has in store for us in the form of overflow and underflow that programmers should be aware of. So make sure you revisit those videos for these concepts, because these videos will also help us understand the upcoming flag, that is the overflow flag. So the overflow flag is a very useful flag that signifies the overflow status to caution the user that the sign of the result has changed unexpectedly. The overflow flag F is also only used with signed numbers, okay? For example, if we add two 4-bit numbers, and we know what are the ranges of, for example, if we add two 4-bit signed numbers, and we know what are the ranges for a 4-bit signed numbers, both positive and negative numbers. For positive, we have the range from 0 to 7, and for negative, we have the range from -8 to -1. Suppose we add these numbers and the sign in the destination changes unexpectedly. So the OF is set high. That is, it is set to 1. And otherwise, that would be set to 0. For example, the highest number in 2's complement that could be represented in a 4-bit sequence is equal to 7. If you would add 7 to 1, that would give us 8. and 8 cannot be represented in a 4-bit binary number. And if we notice in the binary arithmetic, that would generate a carry all the way to the fourth bit. That is the most significant bit, which results in changing the sign bit from 0 to 1. The OF would get updated by the processor to 1. That would caution the user to take corrective measures. Okay. The overflow flag seems very similar to the carry flag, and most of the people get confused. The overflow flag is slightly different to the carry flag in that the carry flag is used with unsigned integers. But since in most computing systems we use signed arithmetic, right? So the overflow flag is used with signed numbers to inform us whether an overflow has occurred or not. Let us talk in a little bit more detail about the overflow flag. And for this, we would require a much larger area. So this is now our workspace. And also recall that in the carry flag, we were actually talking about carry that was in fact carry out from the most significant bit, right? But there is also a carry into the most significant bit that is called carry in. And if we go one slide back, in this example, we had 7 plus 1. We have a carry in into the most significant bit, but we have no carry out from the most significant bit. So coming back to our slide, there is an important observation that the overflow flag is really the XOR of the carry in and carry out. So let us verify this claim using these examples with various combinations of carry in and carry out. Okay, but keep in mind that since we are dealing with the overflow flag, these values or numbers are in 2's complement. And also, to make things simple, we are considering 4-bit number, which has a range of -8 to 7 to +7, right? So we will consider different values that would cover all the possible combinations of carry in and carry out. In the first instance, we have 7 plus 3 in decimal and their corresponding binary representation in 2's complement given on the right, okay? And we get 10 in decimal, but we cannot represent 10 in 4 bits, as we know that the maximum we can have in a 4-bit number is +7, right? Therefore, we expect an overflow. So when we do the arithmetic in binary, we notice that we have a carry in, but no carry out. I hope you agree with that. So this gives us a rule. If there is a carry in and there is no carry out, then we get an overflow, meaning that the overflow flag will be set to 1. Okay. In the second instance, we have -7 and 3. So when we add, we have the result -4 in decimal, which is perfectly right, because -4 lies inside the range of a 4-bit number, because we know that in 2's complement, the range is +7 down to -8. Okay. So we don't have any overflow here because we don't have any of the carry, either in or out of the most significant bit. And 0 XOR 0 gives us 0, meaning no overflow. Then we have a very interesting case where we have 7 and -3, which gives us 4. And we know by now that there is no overflow. There is no overflow in this case. But just look at the binary arithmetic here, and we will notice that we have both carries, both the carry in and carry out. But since in XOR logic, we cannot have both inputs as ones or zeros, therefore we have no overflow for cases with carry in as well as carry out, as in this case, or no carries at all, as in the previous case. Okay. In the last case, we have a carry out from the most significant bit, but no carry in into the most significant bit, which means that we have an overflow. And hence, it has been verified that overflow is really an XOR between carry in and carry out. And these are the related instructions that are used with the overflow flag. JO, jump if overflow, JNO, jump if no overflow. And there is a special instruction named into, that is interrupt on overflow. So this instruction actually generates an interrupt if there is an overflow. Okay. But now, how does the system know about signed or unsigned? Or in other words, how does the processor know the different interpretations? Well, it doesn't. The processor simply sets the carry and overflow flags that can be used with their related instructions. However, the compiler need to be instructed about the kind of data type that we intend to use. So, so that it can select the appropriate instructions for implementing your program. It is very important to grasp this concept, okay? So when you tell the compiler what data type you are using, the system actually gets to know which interpretation is required for translating our high-level code into the machine code, okay? So this completes the picture of the difference between the carry and overflow flag. I hope that was cool. So this was all about conditional flags that we saw in detail. Now there are three control flags that are used by the processor to control various modes of the processor. For example, we have this control flag called trap that plays a very useful role in debugging your programs. And what does debugging programs really mean? Well, the word bug actually mean an error in our programs, and debugging means to correct that error. And by now you must have used a debugger called GDB in C programming language, right? So a debugger actually helps us execute our programs one instruction at a time and pauses for a while to let us see all the values of variables and registers to see if the code that we have written is working as expected. So if the trap flag is set to 1, it is set to be in the trace mode or the break mode or single step mode. Okay, these are interchangeably used in place of debug mode, which means that after an instruction is executed, it waits for us until we give it a go ahead to execute the next instruction. And during this pause, the user can now look at all the variables, all the register values, and see if things are working as intended. Okay, so you are able to trace what is exactly happening internally in their code. And the trap flag, if set to 0, means that we are not in the debugging mode. We are in the go mode. That basically means execute instruction sequentially without breaking or discontinuing. Then there is another flag called interrupt flag. An interrupt basically, as its English says, to interfere. When an IO device, for example, wants to interrupt the flow of execution of the program to send some special information to the CPU. Now, if the CPU sets the interrupt flag to 0 as part of its program status word, that means it is not willing to take any interrupts from the IO device. The CPU has disabled all the interrupts and don't want to be interrupted. So even if the IO device sends some interrupts or some signals to request interface, those signals will simply be discarded, right? Similarly, if the interrupt flag is set to 1, it means the interrupt is enabled. Now the IO device can communicate with the CPU by sending interrupts that would now be serviced by the CPU, okay? So long story short, this flag decides whether we want to be interrupted or not by setting or clearing this flag. One important fact about this flag is that this is not in control of the processor because the user really knows when to interrupt and when not, right? Then we have this flag called direction flag. That is a very useful flag and is very specific to string operations. Recall that the string data type is a sequence of characters. Recall that the string data type is a sequence of characters that are one byte entity. And most of the time we are dealing with string operations that basically include copying strings, string concatenation, string comparisons, etc. So this flag is mostly used for string operations, okay? For example, if I want to read a string from the memory, right? And I set the direction flag to 0, that would imply that I want to access the memory from lower addresses to higher addresses to construct the string. And mostly the direction flag is set to 0. But again, depending on the application at hand, we can also set the direction flag to 1, in which case the access would be in reverse order from higher addresses towards lower addresses. For example, this is what I have in my memory, DIVE at addresses of 100, 200, and 300. And if I set the direction flag to 0, then we would read in this order, and we have DIV. And if the DF is set to 1, then we read in the reverse order, and we get vid. So this brings us to our last slide. These are all the flags that we have as part of the program status word. Again, remember that we have discussed the flags of the 8086 microprocessors, and different microprocessors have different flags. However, what we discussed here are generally some of the most important types of flags that are there in almost every modern microprocessor. And these are the rich set of x86 instructions used in implementing conditional logic. These are the instructions that utilizes these flags either alone or in a mix of logical combinations and enable our compilers to implement the broad spectrum of complex high-level logic into machine code. These are the instructions that we already know from our crash course on x86 assembly. And this is it for this session. And I hope you enjoyed this video. In the next video, we will talk about how stacks are actually used in function calls in x86 assembly language. Thank you.